All right, so relative motion. This is very. This is relative motion is it's a one-dimensional motion type problem. So it appears in the 2D chapter because you can do 2D problems with it. But we're gonna try to keep. Oh no, we're gonna do 2D problems. Never mind. Okay, whatever. In the figure here, at the bottom, we have three different observers. And these observers will say different things about how things are moving. Okay? So Amy sees Carlos move at 5 meters per second and Bill move in Bill's car at 50 meters per second. The way that we indicate this is we will say V sub x CA is positive 5 meters per second. Now the CA means Carlos relative to Amy. So the first letter is the object and the second letter is the observer. So that's what Amy sees. According to Bill, though, Bill sees Carlos's velocity to be minus 10 meters per second. Again, the subscripts mean Carlos relative to Bill. Okay, so you can see these numbers are different, right? We're both both these people are observing Carlos, but they report different speeds because they are themselves moving relative to each other. And so, this is something that's a very famous problem in physics, that we don't have true reference frames for motion. I mean, the only true reference frame we could possibly have is the cosmic microwave background radiation, that it permeates the universe, and that can actually act as a reference frame, but that's ultimately is still relative. It's just a very large, pervasive kind of radiation that exists in the universe. But anyway, that's a whole other topic. Take me for astronomy if you care about that stuff. But anyway, so now here's the thing, though. Are they wrong? They have different numbers, right? But are they wrong? They're not wrong. They're not wrong. And so what we want to do is we want to create a system where people may disagree about the actual speed of an object, but there should be a system where they can check each other's speeds and then verify that they are witnessing the same behavior. And that's really what we're trying to do here. So trying to create a system that helps us do that. So let's get into it. Here we have two different reference frames, and we have an object. Reference frame A, reference frame B, and they're trying to observe an object located at C. And we can define several things right now. We can define the position of C relative to both reference frame A and B, and we can define a position vector that describes how A and B relate to each other. Now you can see the way this triangle looks here. We can write this out as a vector addition. And as you can see here, vector RAB added to vector RCA is going to be equal to vector RCB. So this equation right here is the means by which two people could verify that they see the same thing. They both report different positions, but when you incorporate the position vector between the two reference frames and apply this equation, they can see that they are talking about the same object. And so this is how we're going to first formulate this. What we can do with these positions, we can use the definition of velocity on this, right? So we can take the time derivative of this equation here. The rate at which the position is going to change here, it will be equal to the speed. So this same relationship for the positions can be related to velocity. So it's the same exact equation, same subscripts, right, with velocity. And this is what's known as the Galilean transformation of velocity. And two people can observe an object and they may report different speeds for the object. But this equation allows them to check their numbers and make sure that they're observing the same thing. So again, let's read what this says here. The velocity of object C relative to B is going to be equal to the velocity of object C relative to A plus the frame velocity. So this frame velocity here, VAB, this is the velocity of frame A as seen by B. So let's say A is heading over to the right here at, say, 30 meters per second. We would put in a 30 I hat meters per second to the VBA. Now, due to relative motion, though, guess what? Oh, I think I actually have this in a slide. Hold on. Oh, I do. I am so happy when my current thoughts match up the thoughts of the past when I made this slide, because I have some small indication that I'm not slipping into any kind of dementia, which I'm glad I'm not. All right. So, I was just explaining what these things are here. You can kind of view the way the subscripts are written, you can kind of view it in the way that they show here. Velocity of C relative to B, it makes sense that if you add these two together, you would get that, because what you're doing is just saying, what is AC? And then add that to what A is doing. And that's what B is going to see. That makes a lot of sense when you think about it that way. So that's pretty cool. Okay. Now, what I was trying to say before here is, due to relative motion, right? If we see frame A moving to the right at a particular speed, what you know, so if A is moving, say, 30 meters per second to the right, well, guess what A is going to say? A is going to say, well, according to me, I see B move at the same speed in the other direction. So if you were to swap the subscripts here, you can do that by simply throwing a negative sign right in the front of it. Because again, if one is moving 30 meters per second one way, according to one, the other one's going to say that the other one's going at that speed in the other direction. And that's why we're able to justify that thing. Okay. Let's do a problem right now. Yes. Example number 1. Let's bring it up. Here we go. So we have a runner, and they're observing 2 balls. Now, one of the things you want to do in these problems is this. I have an organization here that I highly recommend to you. And here's the organization. You want to write the equation out, right? And then you want to properly identify what A, B, and C is going to be. Now, C is always the object that we're trying to observe. And that would be, in this case here, one of the balls. Okay, in fact, there are 2 objects in this, and we're going to do 2 problems. So for the first, we're just going to choose ball 1 as our object. Now, B is our stationary frame. So that's like you watching this thing happen. Okay, this runner's getting, hit. They're getting balls thrown in for some reason. And then A is the moving frame. That would be the runner. So a person standing by watching this take place has a statement about what's going on with these balls, and the runner has a statement. Now, in the problem, it says, according to the runner, both balls are approaching at 10 meters per second. So that means we know what VCA is. We know VCA, right? We know the speed of the ball relative to the runner. So again, if you really clearly identify what is C, what is B, what is A. C is always your object. B is always a stationary frame. A is always the moving frame. Make sure you clearly identify that so you know what numbers to put where. Okay, now, so let's apply this to ball 1. Now, these are velocities, to be certain. So you need to put in appropriate positive and negative signs depending on which way things are going. Okay, So v sub b, we want to know what the speed of ball 1 is relative to a stationary frame observer, relative to the ground, right? So c sub a, v sub ca, let's say that, vca, is 10 meters per second positive. The runner is moving at 5 meters per second. So according to the equation, we would add them up, and it's 15 meters per second. Okay. Now that makes sense, actually, because if you are moving in the same direction as an object, it will not appear to move as fast, right? Because you're moving along with it. So the runner sees 10, we see 15, and that makes sense. Okay. Now ball 2 is moving toward the runner, so the runner is actually going to report that as a negative 10. So we'll put a negative 10 in here. Of course, the frame velocity is the same, 5. We add these up, we get a minus 5 meters per second. Okay, now this makes sense because look, this ball is moving toward the person. They're approaching each other. Okay, when two objects are approaching each other, it's going to give the appearance that it moves faster than it does relative to the ground. Okay, so they see 10, but we see 5. And that extra 5 is due to them moving toward it. So the position between the two objects, gets sufficiently closer and closer. But anyway, that's applying, the equation to the situation here. And really the challenge in these problems is this first step, just being able to identify what is what. Because the math, as you can see, is pretty straightforward. All right. I will say, though, that in these problems, the thing I mentioned a little earlier, in order to conceptually understand what's going on here, is very helpful. If you move with an object, it doesn't appear to move as fast. If you move, if an object is moving toward you and you're moving toward it, right, it will appear to go faster. So that's kind of a general conceptual rule. I mean, it always will pan out in the math. But let me ask you, do you have any questions about this problem? Does this kind of make sense?
Yeah, so the object is the ball and the moving frame is the runner. What is the stationary frame?
That's just the ground. We just call that the ground. That's just
okay.
The person was, so the ground is about as much of an absolute reference frame as one could possibly hope for. And there's always going to be, I mean, we don't have to have a stationary frame. It's just most of our problems involve talking about a stationary frame, so yeah.
Okay. Thank you.
Yep. Anything else?
Just to be sure, ball 2 is negative because it's facing to the left.
Yes, right. It moves to the left. All right. Okay, let's get back to. All right, I got a question for you. Got a factory conveyor belt rolls at 3 meters per second. All right. You got this tasty looking cheese right here, and this mouse wants it. So the mouse is going to run toward it at 4 meters per second. Now the conveyor belt itself moves at 3 meters per second. Now say you're working in this factory and you see this mouse and you're like, damn it, the inspector's going to be here in an hour. So you got to make sure you get this mouse. So imagine like you're looking down on this. What are you going to see the mouse doing from your perspective, from like a ground perspective, basically? What do you think's happening here? Letter in the chat. Now there's a super easy way to do this problem and a slightly less easier way to do this problem. But I want to see some letters. A lot of people saying A, but it's not A. It's not, and I'm not joking. It's not A. Now everybody's coming in with the C. All the sheep coming in with the C. It's not C either. It's D. It's D. It's D. Now, here's the easy way to do this. The mouse is already moving at 4 meters per second. If it jumps on the belt, it's going to be moving faster. So the answer is D. That's it. I mean, that's the easiest way to determine that it's D. It's the only speed that's faster than the mouse speed. Okay. Now, the figure down here, though, shows what's going on. Now, the mouse, right? The mouse is the object. The mouse is the object. The floor is the ground frame, and the belt is the moving frame. So we're trying to observe from the ground frame what the mouse is doing. Okay, the mouse is going 4 meters per second. Not according to you, who's watching it. According to somebody who's just hanging out on the belt watching this all take place. Yeah, it is a Pythagorean triple too, actually. Yeah. So yeah, be careful about what we say here for 4. The mouse is on the belt, moving 4 meters per second. And that's the speed relative to the moving frame, not relative to the ground. This velocity vector that you see here is the velocity of the object as seen from the ground. Now, this is a two-dimensional problem. As soon as it becomes 2 dimensions, you're going to want to throw some vector notations on these things. But you got VMB, right? That's the mouse relative to the moving frame. That's 4. And we would say 4 I hat. And then the velocity of the moving frame relative to the floor, that's the frame velocity. That's a minus 3 j hat. If I decide to make a coordinate system that looks, I mean, just a standard coordinate system like this, you know, if I do my x and y like that, well, then it's going, you know, minus 3 j hat. And of course, due to the fact that it's a Pythagorean triple, we know the magnitude of this is 5. Okay, so as you look down and you see this mouse going, it moves at an angle, right? It goes right and down, and if you were to properly measure how fast it was going, it'd be going 5 meters per second. It does 4 on its own, but that 3 downward gives that a little bit of extra push there. So, okay. Any questions about that? This is a good problem. This makes you think. But you know, the examples for you, like, I get that. Well, this one's a little different. This one makes you think a little bit, so I like it. And who doesn't like cheese? Vegans don't like cheese, so.
Where do you determine the floor?
Where do I determine the floor? Oh, again, the floor is just the ground frame, right? It's just anybody who's not on the belt, pretty much. So,
Oh, okay.
yeah. Okay. Let's do this one. This is a very similar problem. Susan's driving north at 60 miles per hour and Trent is driving east. All right, so let's visualize this. What do we got here? Yeah, ceiling would be fine. Unless you got one of those crazy factories where the ceiling moves relative to the ground. I've never seen a factory like that, but I'm going to be optimistic and say that maybe somewhere in the world there's one factory like that where the ceiling moves too. But assuming the ceiling and the floor don't move together, you can see the ceiling. That would be perfectly fine. Or you could say, I mean, I'm imagining like some person's up on like a railing or something and looking down at this mouse and like, damn it. And they're just, and for some reason, without solving the problem, you know, for some reason they're not trying to catch the mouse. They're like, I want to do a little physics right now. I don't want to deal with the mouse. I just want to know how fast it moves. So, all right, what's Susan doing? Susan's going north, 60 miles per hour. That's Susan. What's Trent doing? Trent's going east, a little slower. Like that, maybe. They're approaching an intersection. What is Trent's speed relative to Susan's reference frame? What do you think Susan's going to see here, right? I mean, you clearly see Trent moving to the right, but you're also going to see Trent moving down. So I'm going to draw this in a different color, but what Susan sees is something probably like this. Like that. Because again, I mean, you got to think about what if you're approaching an intersection and a car's coming, right? You're both approaching an intersection. Again, just, you know, take out the background here, right? Forget that. this thing would look like it moves to the right, and it looks like it moves towards you, right? Another way to think about this: imagine you're just like in the middle of deep space, right? And you're just chugging along in your spaceship, and then there's this other spaceship that's moving, perpendicular to you, right? Without any external reference, what does that ship look like it's doing? It looks like it's going right, and it looks like it's heading toward you. So we want to figure out what that speed is. So let's look at. All right, I drew the little picture right here. The object is Trent. The object is Trent. B is the stationary frame. A is the moving frame. That is Susan. Now the stationary frame, that's what these numbers are. When we say Susan's going north and Trent's going east, these speeds and directions are according to the people that maybe is at the intersection watching the horror about to take place as these people collide together. Okay? So once we identify those three things, now we can jump over to the equation. You write the equation out and then very carefully follow the subscripts. The velocity of CB, that means the velocity of Trent relative to the ground frame. We know that. That's 45 I hat. We don't know CA, right? We don't know what Trent's doing according to Susan. We're going to figure it out. But we do know that the velocity of Susan relative to the ground frame, that's what BA is 60 J hat. And so we'll have to move we're solving for the question mark here, right? We're solving for VCA. So we're going to move the 60 J hat to the other side, gets a negative on it, and then another Pythagorean triple, 45, 60, 75. It appears to go 75. And you could work out an angle if you care. You could work out an angle, right? I mean, we have the vector here, so any kind of angle you want to define. I mean, you could draw a triangle like this, and you can maybe talk about this angle that's like right here. But this just asks for the speed, 75. Okay, so one thing that you might notice, like a consistent thing you might notice in these problems, it really matters how you draw things out, and it really matters how you define your CBA. And it can be a little tricky to understand what goes where. But sometimes it's easier to figure out two of the things, and then you realize the third thing has to be this, right? So, figure out what the object is and figure out the two things that are watching, right? Figure out what's the object and who are the two observers. And once you can identify that, it shouldn't be so bad, because the math, as you can see, is not challenging. It's the physics. It's conceptualizing everything and being able to apply the numbers to the equation. Any question about this one? Okay.
Hey, can I ask why did you square root the 45 and 60?
Because I was trying to determine the magnitude of the vector. So this is the vector here, 45, 60, right? And so that would be this vector like this, which I'll need to break into components if I want to figure out what the magnitude of that vector is. And these are the components, right? So I'm doing the Pythagorean.
Oh, okay.
Yep. This one is really good. This one's super good. Super good. You'll love this problem. You know why I say you love a problem is because when you look at this problem, you're not going to understand it initially. I mean, if you do, well, by all means, fantastic. That's great. But what I like is you look and you're like, what the heck? What is this? I don't understand this. And then you look at the solution and you ponder it and you think about it and you print out the slide and you keep it in your pocket. And every time you got a free moment, you open it up and you admire it and understand it. And then at some point it sinks in and you're like, I learned something here. And that feels fun. That's just fun. Also, if it feels like a trick question, then I know I'm doing my job. All right. Mary needs to row her boat across a 100-meter wide river that is flowing to the east at a speed of 1 meter per second. Mary can row with a speed of 2 meters per second. Mary points her boat north. How far from her intended landing spot will she end up when she reaches? Okay, great. So, what's the object? Mary's the object. The ground frame is the ground frame. It's somebody standing on the shore here that is rooting Mary on. Go, Mary. I can't wait for you to come to the other side so we can have our barbecue. There we go. This person's awfully happy to see Mary. So they're the ground people. We're watching what Mary's doing, and the river is the moving frame. Now, she's going to try to go 2 meters per second north. She's not going to go 2 meters per second north, is she, though? Because the current is going to take her down the river a bit. So her actual velocity vector is going to be at an angle, which is this vector right here. And as you can see, it's the combination of what she can do and what the river does. So she's actually going to go faster in the river, according to the ground observer, because she's getting a little kick from the river here. The problem with this is that she's not going to go straight. She's going to drift a little to the side. So maybe she's anticipating drifting to the side, and that's why this person's hanging out over here. Go, Mary. So let's do it. What's VCB? That would be Mary relative to the ground. We don't know that. That's what we want to find out. What is VCA? That would be Mary relative to the river. And that's 2. That's 2. Okay? That's what Mary can do. She's in the river. She's going 2 meters per second. If you were in the river too, you'd see her going 2 meters per second. All right? And then VBA is the frame velocity, which is the river. It moves at a speed of 1 meter per second. So the equation is this right here. We put in our numbers. It's 2j hat plus 1I hat. That's the vector. It points up and to the right. But we want to know her speed relative to the shore. So it looks like I'm doing part B first, right? And that is going to be radical 5, which is 2.2 meters. Now, how far north from her intended land spot is she going to be? So basically, I'm asking myself this. How long does it take to go across the river? Because remember, this vector that I drew here is a combination of her trying to go north and the river pushing her to the east. So the question becomes this. How long is it going to take her to cross the river? Because in that amount of time, she's drifting east. So if going at 2 meters per second relative to the river, and you want to go 100 meters, that's going to take you 50 seconds to do that. Okay, so if the river is pushing you at 1 meter per second for 50 seconds, you're going to end up 50 meters downstream then. So maybe she anticipated that, knowing how fast she can go and what the river's doing. She sets up 50 meters, back. And, yeah, and that's how we figure out part A there. Okay. Now, it's a good problem. It's not a simple problem. I mean, it looks simple, but it's harder to put these things together. So let me ask you, do you have any questions about this problem? I might have a few more things to say about it, actually, but do you have any initial questions about it?
So why are we're just dividing 100 by 2? Why wouldn't we do 2.2?
Oh, because relative to the river, right? Because we're trying to figure out her going north here. And what constrains how long she's going to be drifting for is what she can do just going north. You can, by the way, if you want to, you can work out 2.2 meters, but you'd have to incorporate the direction. You're going to have to incorporate how far across the shore is. It's a lot more work if you do it that way. You can do it, but it's going to be a little bit of a headache to do it. Because you're eventually going to have to work out, what the component of this vector is, vertically or in the north direction. Well, we already have that though, so it's just extra work. It's not wrong. It's just, so. All right. Anything else?
Could you explain part A again?
Yeah. So the idea here is, let me show you their path, right? This is their path. This will be like a displacement vector, right? Bam. That's it. Okay, now that needs to be split into components though, right? There is this component, which is what Mary can do with her. Is she in a canoe? Do we know that? Yeah, a boat? I mean, a boat's a canoe. Wait. Switch that, reverse it. Okay. And then moving to the right is what the river's doing. So you have to break this into components to figure out, how long it's going to take. Now, there's no acceleration here. This is simple rate times time equals distance, right? So that's how we're figuring out 50 seconds. I mean, it makes sense, right? If you're going 2 meters per second, 100 meters, 50 seconds. I don't need an equation really to do that. But then if I realize it takes 50 seconds, well, what happens in 50 seconds? The river pushes you along 50 meters because it goes 1 meter per second. So that's all that is. But it really helps to draw that out. I mean, really, I think so. I think it makes it really clear when you see what's happening here. Okay. All right. Anything else? Okay. Now, you have a homework problem that's like this. Except here's the thing. Say we don't want to drift down the shoreline. What are you going to have to do to prevent yourself from drifting down the shoreline? You have any idea?
Yeah, you'd have to go like the opposite, or not really the opposite, but you'd have to go to the the left more.
Right.
You wouldn't have to go straight.
You're trying to compensate for what the river's doing. So guess what? If you want to make sure that you do truly maintain a northern direction, your velocity vector is probably going to be at an angle like this. And guess what? The y component of that vector has to match the river. If the y component of this vector matches the river, you've canceled out the river's effects. It's just going to look funny. You're going to be pointed at an angle, but you're going to go straight across.
Wouldn't it then be like the same, I guess, velocity or rate going the other direction, but it would be like, I guess, negative in this case because you're pointing to the left?
I mean, yeah. I mean, that component. So, for example, the velocity vector, just instead of having a +1 here, you put a -1 in here. And that would give you the appropriate vector if you're trying to cancel out the river. So that's the problem that you have in the homework is you're deciding. I think the problem is what angle do you need to orient yourself to make sure that you go straight across. So I think that's the homework problem. So you want to really pay attention to how this was done. Anyway, okay. So I'm going to move on because we got to move on. So now this is as much as we're going to cover about relative motion for now. I got some more things to say about relative motion a little bit later in the class. And of course, if 211 is in your future, well, that's special relativity is in that class. Where everything you ever thought you knew is wrong. About everything. Okay. Awesome. Let's move on. Don't ding at me, computer. How rude. All right. Now, next topic. Circular motion. Are you ready for this? I don't think you are. All right. Now, circular motion is a problem that we are going to do a lot in physics. You're going to see circular motion pop up repeatedly over the course of the semester. And especially when you get into the other physics classes, this is just a really core idea. Okay, now, the simplest type of circular motion is what's known as uniform circular motion. Just like uniform circular motion, where you maintain the same speed at a constant radius. And with that speed, that speed can be defined with respect to the distance you travel in the circle and the amount of time it takes to go around the circle, which is what we call the period, and that's indicated with a capital T. Not a P, capital T, because capital P is used for too many other things. So we got T, it's like time, but it's not. But it is, it's units of seconds. So one way to talk about the speed of uniform circular motion is to state the circumference of the circle and the amount of time it takes to go around. That's one way you can talk about speed. Okay. Now, this, however, when you look at this, I mean, you may initially say, it's not, this is not, you know, one-dimensional motion. This is a two-dimensional motion problem. But when circular motion stuff is occurring, we don't want to think in terms of like X and Y. We can turn it into a one-dimensional problem if we recognize that we can use a polar coordinate system instead of a Cartesian coordinate system. The polar coordinate system will have a distance, that's the radius of the circle, and an angle indicating how much you've moved along that circle. Now, r is constant, right? So the only variable here is the angle, right? And so all the problems that we've done one-dimensionally will apply to this. Just realizing that your position isn't actually an angle, right? So now this formula down here, this is something that you've hopefully learned from, you know, your math classes, this is geometry and trig and things like that. But the actual distance traveled, the translational distance traveled, this would be the meters portion, is related to the angle by the arc length formula. So the radius of the circle times the angle here is giving us what that translation motion is. And this equation should be understood as a way to translate between the two, translational motion and rotational motion. And the relationship between the two is simply radius, right? Now, that one thing you got to remember about this equation, though, this equation requires you to use radians. You cannot use degrees for this. Okay, when an angle occurs outside of your trig functions, you can only use radians. Okay, you can't use degrees. It's just straight up wrong. It's just wrong. You're gonna get the problem very wrong if you use that. So my advice to you is to not use degrees. Okay, that's my advice to you. Let's go. Let's keep going. All right, so now we're going to develop all the other ideas based on this. Now we've identified what our equivalent of position is, and so now we can apply all the other ideas we have. If angle is position, then a delta theta represents an angular displacement. And then once we have our concept of displacement, we can turn that into the concept of angular speed or angular velocity. So the definition of angular velocity is the ratio of delta theta to delta t. And of course, the same thing applies if we take the limit as delta t approaches 0. That is the derivative of theta with respect to t. And if the derivative is constant, that is true uniform circular motion. Whereas the definition with the deltas is just an average. Okay? But if the derivative is constant, then the instantaneous velocity is truly uniform. This symbol that you see here looks like a W. It's Greek letter omega. And that's the symbol we use for angular velocity. It has units of radians per second. Radians per second. So, now, there is a little difference from the translational motion stuff to this. In the translational motion, you have a little bit of freedom on how you can define your coordinate system, right? Normally people say right is positive, left is negative, right? Up is positive, down is negative. But you are free to change that as long as you're consistent with the change. That's not true here. There is a standard that is used, and you really need to stick with the standard. And the standard is counterclockwise. Okay, counterclockwise is considered positive. So as terms of an angle, in terms of motion, counterclockwise is always the default. It's positive, and clockwise, therefore, is negative. Okay. Now, all the same principles apply, though. Okay. If you have graphs, right, the slope of a angular velocity graph, right? The slope of a position versus time graph, if it's an angle, is going to yield what omega is, and if it's positive or negative, that tells you the direction of rotation. And this kinematic equation down here applies. Now notice this kinematic equation is identical to what the other one is, it's just replaced with the appropriate symbols. So instead of having position, we have an angle here. Instead of having v, we have omega. Okay, simple enough. All right, so based on that, oh no, where are my letters? Oh, this is horrible. All right, well, let's just say that the first one's A and the second one's B and so on. How about that? We'll do that. Okay, this is the angular velocity graph of a wheel. How many revolutions does the wheel make in the first 4 seconds? Notice the units here are revs per second. You can do that. It's not standard, but you can get away with it. Remember, what you're doing is, again, go back to the stuff we did with graphs. If you have a velocity graph and you want to figure out displacement or position, you got to work out areas, right? You got to work at areas. Okay, C is a very popular option. Well, each box is what? 1, right? So, thanks, Sergio. 1, 2, 3, 4, 5, and the 2 triangles make 6. The answer is C. All right, good stuff. That's just a refresher from before. All right, here we go.
Could you explain that?
I worked out the area. So let me trace it out here. Right, when you're going from a velocity graph to a position graph, you're working out the area bounded by the graph. So I worked out, well, this area right here. And it turns out each box is an area of 1 revolution. And this is a half. And this is a half. So we got 6 altogether. That's how many revolutions were made. Good stuff. Good stuff. Okay. Any other questions? Clear my drawings. Okay. All right. So, oh my, I got this right here. Okay. Now, now the equation we had before was the following here. Is this hooked up? Does this work? On. Let me see if this works. Yeah, it does work. Okay, so the equation we originally developed was this. V equals 2 pi r over t. Okay, now we had previously this equation here. This is the arc length equation. But when you apply this to velocity stuff, this becomes V equals R omega. So that's a translation between, well, that's the relationship between the translational motion and the angular motion. By the way, there is one for acceleration. It's A equals R alpha. Sorry, my drawing tablet does this thing where it just draws these lines. I've never figured out what's going on. I've never really got into the drawing tablet too much. I don't know what's happening there. But anyway, so those lines don't mean anything. But anyway, at A equals R alpha. And alpha is an angular acceleration. So S is position, V is velocity, A is acceleration. Theta is angular position, angular velocity, angular acceleration. And you can see the relationship between all of them is R, right? Now, if that's the case, then I can divide this equation over here by R, and that's how I get the following equation right here. So divide everything by R gives me omega, 2 pi over t is omega. It's another way to, so if you know the period of the motion, you automatically know what the speed of the motion is. Okay? So, because the units of omega, right? Radians, or you can do revolutions per second, but this is for radians, but radians per second. That's the units here, right? 2 pi over t. That works. Okay. So, question for you here. Put this in chat. I got to step away for 1 second because I got to grab something. C's. Is it C? It's A. What happened here? Everybody's saying C. It's not C. Let's see here. Ball rolls around a circular track with an angular velocity of 4 pi radians. Well, that's omega. It's 4 pi radians per second. The period of motion, therefore, right, would be 2 pi over omega. So that looks like 1/2. That makes sense though, right? Because 2 pi is the circumference, right? So if you're doing 4 pi, you're doing that twice in a second. So 1/2 second is the period. Is that is there anything confusing about that? Because I saw a lot of C's up in here.
What is the T stand for again?
What?
What is the T stand for again?
Period.
Period.
Period. Yeah. Why are all saying C? I don't understand it. All
And then
right.
omega is W, right?
Omega is angular velocity. We're just trying to follow. Yeah, no, it's fine. It's fine. Flip the division. Well, that makes sense. Okay. Excellent then. Oh, okay. How are we doing on time here? Ooh, really good on time. An old-fashioned single-play vinyl record rotates at 45 RPMs. What is the angular velocity in radians per second, and what is the period of the motion? Now, one of the purposes for this problem is this conversion from revolutions per second, RPMs, to radians per second. Now, revolutions per minute is a very common way you would explain how fast something rotates. It's just a very common descriptive, way to describe. Well, I mean, it's a number, but still, it's a unit that's very commonly used. But we can't use RPMs typically in our equations. They require things to be strictly SI. That would be radians per second. So we have to do that conversion. So let's look at that. Okay, so omega is 45 RPMs. I'm going to write that out as revolutions, rev, per minute. But I'll need to multiply that by a conversion ratio. I got to go from revolutions to radians. So I'm going to be multiplying by 2 pi radians over 1 rev. That converts into radians. And then I got to multiply by 1 minute is 60 seconds. And that changes my units to radians per second. Now you'll notice what I'm doing here is I'm multiplying by 2 pi over 60. Or you could say it's pi over 30. But that is converting from RPMs to radians per second. Pi over 30. Or I like to say it's 2 pi over 60 because the 2 pi and the 60, it's part of the conversion. Having it simplified, just, you can do that. And so multiplying those two together is going to give you what the radians per second is, which just happens to be 3 pi over 2. Notice I left it as pi. A lot of times you don't need to actually type out what pi is or figure that out for a couple of reasons. I mean, leaving things in terms of pi is certainly reasonable. And also, a lot of times you use those numbers in other equations, and the pi will cancel out anyway. So now you see I multiplied by pi over 30 to go from revolutions per minute to radians per second. What do you think I'm going to have to do if I want to go the other way? If I want to go from radians per second to revolutions per minute, what am I going to do there? You have any idea? Anybody?
You do the same thing but backwards?
Yep, you multiply by the reciprocal of this, 30 over pi. 30 over pi. Yep. So.
Yep.
All right, now I want to figure out what the period of the motion is. The equation for that is 2 pi over omega. So I put in my omega here. Do math. 4/3 seconds. 4/3 seconds. You could put it in 1.3, but I just put 4/3, so that's fine. Now, what could have explained the last question, why a lot of people got it wrong, and one thing you'll notice is, as we do more and more of these circular problems, there's a lot of equations. There's a lot of little equations that convert between things, and that can be a little annoying with this, is trying to keep track of all these equations. So, okay, let's keep going, though. We're almost done here. Oh, well, I already said this, didn't I? I did. So this was the equation I had mentioned before. Now, this v sub t means, well, you could actually state it a couple ways. Tangential velocity, meaning what's the speed at that instant, you know, because like when you move it in a circle here, the way we would define the velocity vector is a tangent to the circle here. It represents what the speed is at that moment. You don't want to draw a velocity vector that somehow gets curved. That's not correct. It would be very wrong if you decide to make your velocity vector like that or something like that, like a curved thing. It's not. Now the angular velocity here, they're showing a direction, but this is not a vector. This is not a vector. So I mean, I almost shouldn't even have this here really, but I do. But it's indicating which way it's turning, but that's not a vector. Not a vector, right? So in fact, we won't even discuss, there is a angular velocity vector, by the way, but we're not even going to talk about that until like chapter 12 or something. It was a long time from now. So, but one thing to notice here is that when you are undergoing circular motion, there is an inherent acceleration that exists. Okay? Uniform circular motion inherently does have an acceleration because you're constantly changing direction. And that direction is center secant. Okay? That's the acceleration direction. And last class we had talked about that, and I kind of showed you how you derive that. So you can refer back to the previous lecture if you're curious as to what this direction is. We call this the centripetal acceleration. And centripetal means center secant. So this acceleration always points towards the center of the circle. It's a constant as well because the motion is uniform. So the acceleration has to stay constant. Right. All right. Now, I'm not going to get much into the derivation of this equation. Your textbook clearly does it. It's a strange derivation. I don't think it adds to your understanding of the problem, so I don't typically go through the derivation of it. Whoa. Okay. So, I mean, but if you wanted to see, you can get a sense of what the how the direction works. If you take two velocity vectors, spaced very close together, you can work out what the delta v is going to be here, and then you have this really thin little triangle, and you can just do a bunch of fun things with that. But again, I'm not going to go through the derivation because I don't think it really adds to the understanding of it. It's just a weird derivation. And I've never really seen, anyway, like a really elegant derivation, one that, illuminates your understanding of the problem or is clever or anything. It's always like a really awkward, strange derivation. But anyway, I'll just say this. The magnitude of the centripetal acceleration is given by v squared over r. V squared over r is the magnitude of the acceleration, and the direction is toward the center of the circle. So I have written this out as a vector, right? V squared over r toward the center of the circle. There is a formal vector notation for this, but I'm not going to introduce it right now. It involves something called an r hat vector. It's a radial unit vector, but we're not going to worry about that for a while. It's just an added layer of complexity that we don't need to go to yet. Now, if it's v squared over r for the acceleration, you can also write this acceleration as omega squared r. If you do the write this in terms of omega, because remember v is r omega. So if you're squaring it, you get a omega squared and you get a factor of r here. So either one is fine to use, v squared over r or omega squared r. And you want to remember both, because remembering both can help you understand a lot of conceptual things. For example, these questions. All right, Rashid and Sophia are riding a merry-go-round that is spinning steadily. Sophia is twice as far from the axis as Rashid. Sophia's angular velocity is what compared to Rashid? Let it in the chat. Okay, so you got to remember, what is the definition, right? What's the definition of angular velocity? Delta theta over delta t, okay? So think about this. Let me draw a line here. Where's my... Oh my goodness. That's terrible. Let's try that one more time. What's wrong? Yeah, here we go. Here we go. Right there. That's like the radius, right? Now at some later time, right? Let's draw at a later time. At a later time, the people are going to be here. There's going to be a dot there and a dot here. Now, in terms of their angle, what has happened, right? What has happened? There are differences to be sure, right? What is this? What are the angles here? They're the same angles. If they're the same angles, then the answer must be B, right? Angular velocity is the same for these two. That's the beauty of angular velocity. Doesn't matter what your radius is, you always go through the same angle, right? So there you go. The answer's B. Oh, of course. Now I see all these B's to the end here. Can't fool me. I got timestamps. I know what's up. All right. Let's keep going. Same setup. So what is Sophia's speed compared to Rashid? What's the speed of Sophia relative? Not relative. What is Sophia's speed compared to? Not relative. Compared to. C. It is C. It is C, because now if you're talking about speed, now look at my drawing here, my beautiful little arcs. You can see that the arc for Sophia was much longer. Yeah, so in the same amount of time, you're traveling more distance. Yeah, you're going twice as fast. Yep, that's why when you go to an actual playground where there's kids, and you start spinning this really fast, the kids at the edge, they're the ones that fly off first, right? And the ones that are further in can, they have a little bit of a fighting chance to stay on. But those kids on the edge, they fly, right? So it's because they're going faster. There's other reasons too. But what's the acceleration of Sophia compared to Rashid, though? What's the acceleration now? Same setup. What's the acceleration? You're going to love this. Whoa, what am I doing here? Here we go. Let's put this back together. That's okay. Aww. You sweethearts. You said B. I'm going to start to cry. Oh my gosh. I can't believe it. Now it's frozen. What did I do wrong? Oh, wait. Oops, I messed up. Sorry. So the best way to think about this, because here's the thing. The v squared over r, it's a little difficult to think about the acceleration as v squared over r. It's much easier to think about this in terms of omega squared r, because we've already established that omega is the same. And so because Sophia is farther away, obviously she has to be accelerating at a greater rate. I don't know what I was thinking. I was all happy that you guys got it right, but no, you let me down. Again. It's okay. I got tripped up there myself. It happens. All right, anyway, just to be clear, the omega's constant. There's different r's, there's different acceleration. And it does make sense, right? Because if you're farther away and you're traveling faster, the rate at which you're changing your direction's got to be increased. That's the idea behind that. Okay.
So the speed in that example isn't what's really like increasing over time because it's like a constant speed. It's mainly the direction. That's why we get the acceleration is faster.
Pretty much, yeah. Because the speed is faster, you need to have a greater acceleration to change your direction. That's the idea.
Okay.
Yeah. All right, we have one last example here. I think Shelby was serving up spaghetti. You guys are hungry. That's what I remember seeing. So, all right. Gregory is working on his bicycle. Has the bike upside down. I don't know why that matters. All right. He spins the 60 centimeter wheel. Now check this out. Centimeter wheel. This is very common in circular motion problems. They just throw in centimeters all the time, and you got to make sure you convert that to meters. Or you can keep it in centimeters, I guess, in some circumstances. You kind of don't want to do that, though. Like, accelerations really got to be in, like, meters per second squared. So anyway. You notice a pebble is stuck in the tread. You notice that a pebble stuck in the tread goes by 3 times every second. What is that telling us? That's actually a concept called frequency. Now, frequency and period are related. They're inversely related. Okay, in fact, it's exactly an inverse relationship. But here's how you should interpret these things. You could think about period. Periods are units of seconds. But what it would mean, it's like seconds per cycle, right? Seconds per cycle is a way to think about it. And then frequency is the reciprocal of that. It's how many cycles occur in a second. So if something goes by 3 times per second, right, that frequency is 3, and that means the period is 1/3. Okay? If it takes 3, if the thing goes around 3 times in a second, then how long does it take to go around once? A third of a second. So it's sometimes nice to think about these in terms of these, things, cycles per second, seconds per cycle for period, things like that. That's very helpful. Because sometimes in the problem, it's like not exactly clear, what they're trying to communicate with that statement, but they're trying to communicate, period, ultimately. So we can immediately determine what the angular speed is, 2 pi over t, which would be 6 pi. 6 pi, okay? Then the velocity is going to be given by 2 pi r over t. I want to know what the pebble's speed is, so I know the radius, I know the time. I end up getting a 180 centimeters per second or 1.8 pi meters per second. There's a pi in here. I didn't just left this pi. And then for the acceleration, you're going to do v squared over r, or you can do omega squared r. And I happen to do omega squared r because I worked out what omega is already. I mean, I could have used this one here, I suppose. Doesn't really matter. But I end up getting 10.8 pi squared meters per second squared. And that's sufficient to do that. So it's pretty straightforward. I don't think it's tricky as the stuff about frequency and period. But otherwise, not too bad. So